Hi everyone, my name is Sohan, and this is my Lab 1 for Physics 2 charged tapes. The purpose of this lab was to essentially show how two charged pieces of clear tape interact and how we can measure that interaction to estimate the excess charge on each piece of tape. To do so, we set up an experiment with the materials listed and eventually verified the results through a glow script model, and the results are listed here, including the charge on each tape and the number of electrons lost by each piece of tape. We can justify these results to three fundamental principles. First, Newton's second law, which states that the net force on an object is equal to its mass times net acceleration. Coulomb's law, which essentially represents the electric force between two objects along a line in between them, proportional to the charges themselves and inversely proportional to the square of the distance between them. And gravitational force, where near the Earth's surface, its mass times 9.8 meters per second squared pointed downward. To proceed with our calculations, we were given several initial conditions. We measured the tape length and width, which allowed us to calculate area. We were given linear mass density of the clear tape, which gave us the tape mass. And finally, we assumed an atom area, which allowed us to estimate the number of surface atoms along our area of tape. Let's define the system with which we collected results. The system was defined as tape B, which was ripped off of tape A such that both of them attained some electric charge. The surroundings were tape A, which held the electric charge, the books holding up tape B, and the earth, which posed a gravitational force on tape B. We also measured that the separation or distance at which the tape started floating was about 0.7 centimeters or 0.007 meters. Using these initial conditions and the experiment setup, we could calculate first the gravitational force on tape B, which is essentially just mass times the gravitational constant. And based on the free body diagram to the right, the magnitude of electric force is equal to the magnitude of the gravitational force. So we equated the two to find the charge on tape B as well, which is shown boxed in the bottom. We can divide the magnitude of charge on the charged piece of tape by the magnitude of charge on each electron to show how many electrons were lost. And then we can take that number and divide it by the total number of atoms on the charged piece of tape, which we calculated before, to get us the percentage or fractions or atoms that gave up electrons. To verify and visualize the results, we created a glow strip model where we condensed each piece of tape into singular point charges, and using the initial conditions of the distance between the tapes and the mass of tape B, we were able to represent the gravitational force field vector and the electric force field vector acting on tape B such that it floated. We verified the charge on each piece of tape as well as the number of electrons lost in the process of ripping the two pieces of tape apart. One reason for pursuing the glow script model was because it was quick and fast in terms of unit tests, meaning we could consistently test the same thing and get the same results to verify our experiment. Now we can discuss how the glow script model compares with our real-life experiment. Both show a like charge repulsion. At the float height, the vertical force is balanced, meaning tape B floats and both the tapes repel from one another. However, the model concentrates charge at a singular point, but the real tape likely has spread, possibly non-uniform charge, and different electric fields at different points along the tape. The strip itself can bow or tilt, which changes the true center-to-center distance between the pieces of tape, and additionally, because we're not in a vacuum, the dielectric constant may not exactly be 9 times 10 to the ninth. It's an estimation. The significant differences between our glow script model and the actual experiment underline several assumptions and sources of error in our experimental process. Firstly, we approximated each piece of tape as a singular point charge to turn a multi-charge problem into a solvable equation for Q. However, it is likely that each piece of tape had extended non-uniform surface charge, meaning the electric field acting on tape B was different in magnitude along its area. Additionally, we assumed that each piece of tape to have an equal magnitude of charge. This allows us to turn a two-variable equation into a single variable equation and solve for Q. But since each piece of tape was handled differently and imperfectly, it's likely that one of the tapes lost more charge than the other. After understanding our experimental results, we can surmise on several different hypotheticals. If electrons were positive and protons were negative, like charges would still repel and unlike charges would still attract, which means that field arrow conventions would flip, but the overall forces, motion, and experimental results would be identical. The reason why we handle the charged tapes as little as possible is because touching the tapes provides a conductive path through the skin, moisture and oils in our fingers, letting the excess charge flow and neutralizes each piece of tape, which disturbs the experimental results.